How's everybody doing?
Doing pretty good.
Great. So let's, oh, I got a thumbs up from Clint. Nice. All right, this is just a kind of a review or recitation kind of a setting today. So I guess I'm open to just about anything you guys want to talk about.
Dr. Scott, if I could ask a quick question. I'm just still having a little bit of trouble understanding how we compute the mass matrix from quadrature points. I'm just trying to work through a lot of the examples that you have in the notes, and I'm just kind of struggling seeing how those mass matrices were computed. Could you just give me a little review on how that's computed again?
Yeah, I can give you all the details.
Thanks.
I'm gonna make somebody else the host so that I can stop admitting people. Any of the TAs, anybody want to volunteer to be the host?
I can do it.
Thanks, Kyle. Okay, great. Let's just go ahead and admit people as they show up. All right, let's set up a whiteboard and just go through the process of making the algorithm. All right, so I'll assume you know that the mass is an integral n a n b d omega. That's going to be the a-bth entry of the matrix. Are we okay with that definition?
Yeah.
Okay.
Yeah, I understand that.
So let's go ahead and pull this back to the parametric domain. We'll call that omega hat, n-a, n-b, and then we have dx, dxc, dxc. Let's just might as well assume this is 1d because it is in this case. Now we need to write a little algorithm to compute. So we have our matrix M is all the entries. Okay, so the mass. So let's maybe as a little aside here. If we're using polynomials of degree p, what size will the mass matrix be?
It'll be p plus 1.
Okay, p plus 1 by p plus 1. Perfect. And then you've got m11, m1 p plus 1, p plus 1 1, and p plus 1, p plus 1. And then we have our a-bth entry in here somewhere. All right, so we just have to populate that matrix. So let's write a little algorithm. Again, it's like this, there's like this skill that we're kind of developing underneath everything we're talking about in class, which is like, okay, how do I take something like this and write an algorithm to turn it into a matrix? Well, what do you know for sure? If you're going to fill up a matrix, you're going to have to do what? Bare minimum.
Do you have to define the basis or?
Yeah, I'm assuming that we've defined that these are the basis functions, right?
Okay, yes.
Okay, so I'm assuming that you have a routine where you can evaluate your basis.
Yeah.
Okay. But if you're going to fill up a matrix, what's the minimum thing that your algorithm should better do?
I'm not sure.
I mean, you have to visit every entry of the matrix, right?
Yeah.
And so how do we visit a two-dimensional, every entry of a two-dimensional array?
You can look through each row and each column.
Yeah, so why don't we just go like, why don't we go through each row and fill it up? So let's say we index each row by the index little a and each column by the index little b. So we're going to write a for loop for a equal 1 to how many rows are there? P plus 1, right? So that's going to be going down here. And then for every row, what do we have to do? So we're at the 8th row, and then what do we need to do to that row?
Another loop through each element in the matrix.
Yep. So for B is going to be now each entry of the row.
Yeah.
Okay. Now somebody stop me if you don't understand this, or tell me you do understand it or something.
This makes sense.
Okay. All right. So now I'm at MAB. Okay. So I know that I'm at the ABth entry of my mass matrix. So I know that I now have to compute this integral. Right? All right. Well, what's the algorithm to compute this matrix or this integral? How do we compute integrals numerically? What's it called?
Is it quadrature?
Exactly. So we're going to approximate our integral. Remember, we write a sum. I equals 1 to like the number of, let's say the number of quadrature points. And we're going to take our integrand, NA, evaluated at some value, CI, NB, evaluated at CI, DX, DXC, evaluated at CI, and then we multiply it times a weight. All right, so let's turn this line into code. So what does this sum become?
That's you take the variable and add it to that variable on every iteration.
Yeah, so
every time you see a summation symbol, once again, think for loop.
Yep, so this will be a for loop. So we have another for loop. So let's go ahead. This is just our mathematical expression. Let's write a little line of code. I'm running out of space here, but I think I can fit it in. M, A, B. Let's set it like equal to 0. And then we have a for loop. Maybe let me just a second. Let me find a little more space here. Okay, so let me come up here now. So now we're writing this for loop so we have our outer for loops for A, for B, and now let's say, okay, we have some variable, let's set it equal to 0, and then we're going to iterate we say we're going to have a for loop over I equals 1 to the number of quadrature points. And then inside MAB is going to be equal to MAB plus this. Okay, now maybe let's just add a little more details here. Maybe out here you initialize a matrix. So let's say you initialize a matrix M. Let's create a zero matrix that's of size like P plus 1 by P plus 1. So that's just going to be a matrix filled with zeros. And then we can come down and we can, since we know that each entry has already been initialized to 0, we certainly could get rid of this and this and replace it with M at AB is equal to M at AB. Okay, now, is that okay? It should be, yes, is that okay? Are we okay?
Yeah, this helps a lot.
Then even to add a little more detail, we could say, okay, there must be a routine somewhere that gives me these basis functions. And that's why since we need a basis function for every single basis function, that's why we have this compute basis call. Actually, this is an important point. Let me back up a minute. In the notes, what do I actually do? I pull this for loop. Notice that there's 3 nested for loops. The inner for loop is quadrature, but it's actually convenient. The order of the for loops actually doesn't matter. So you can do them in any order you want. It's actually convenient often to move the quadrature for loop to the outside loop, which is what's in the notes. So let's just rearrange things for fun. So let's put our quadrature loop out there. Doesn't change anything. Let's move these guys down. All right, now we know we're at a particular point, so we can go ahead and compute quantities at our quadrature point, and then just use them over and over again inside of these 2 nested for loops. So we can compute our basis at some xci, and that's going to give us, like in this case, let's say it gives us a vector of maybe these guys. Then we can compute the geom. And let's say it's ci, and let's pass in maybe like this and this. And then it's going to return, let's say maybe the vector, the position, and actually this is just 1D, isn't it? So that's not a vector, it's just a point. And dx, dxc. And now you have everything you need for the integrand. And that's it. I don't think there's anything else.
Thanks, Dr. Scott. This was very, very helpful.
It's easy after you do it like 10,000 times.
So question on your compute bases. When I compute my bases, I'm getting out the n, a vector that has, depending on the power that or the power that I'm asking for, up to that. But what is this DNDC?
In the next algorithm that you write, admittedly, you don't, the way that I wrote the notes, you don't actually need this.
But later we will want the derivative of those bases.
Yeah, because you're going to
Okay.
compute dx dxc from the dn dxc. For now, you're just I'm having you essentially hard code in a function that's like 1/2 xc plus 1. You're just hard coding this in and the derivative. But, you know, we don't like to hard code things in. So in the next set of notes, we're going to compute these generic geometric maps from the basis functions themselves.
Okay.
Yeah, and that's basically what finite elements is like a whole bunch of for loops and if statements. So, yeah.
And then a big matrix solve at the end, right?
And a big matrix solve at the end. Yeah, that's what I spent my whole life doing. It's pretty pathetic, I know. Okay, good. I like going through things in detail like that. So what else can I do? Any other questions? Quiet group today. Are we gonna get out early?
I guess I can ask mine now. So I've gotten everything with the coefficients, the plots, everything, but my error is on the order of like 1/10 of a decimal place. And it should be obviously a lot lower than that.
When you increase the degree, does the error decrease?
It doesn't change too much. So I have it right now to where if I have a power of 2, then I use 3 quadrature points. A power of 4, I use 5, 6, 7. And then when I have 8, I use 9 quadrature points. But my error showing is like for my Bernstein, it's 0.1.
Okay, so it's not converging. So that is an error. Would you like to show the snippet of code that you think is the offending part of your code?
Yeah, the interesting thing here, Kirk's been emailing me about this, is that he's got, the right coefficients according to the answer key, and so it's probably just an error in calculating the error. But
it's an error in the error.
yeah.
Okay. Yeah, so if you got the right coefficients, great. Then you know it's in there somewhere.
Mm-hmm.
So
I think I need you to stop sharing in order for me to.
Okay. There you go.
Okay. Okay. So this is at the end. So I've got my coefficients. They all match up. And then I assume this is where it's happening, is at some point after this point. So I calculate my UH. I perform the L2 norm, the absolute value of the difference squared. And then here's the integral equations. And they're all duplicates basically of the different variations. And then I just
So
add up.
is the basis that you're using, are you,
So this would be
yeah. So this is a problem. I think you're using a different quadrature for the basis above than you are in your error calculation.
okay.
I mean, maybe not. I don't know. I mean, you're when you compute the UH, can you go to that again?
Uh-huh.
So that a thing called, I don't know, like burn. What is that, a vector?
That is my basis. So
Yeah, but evaluated where?
pull it up. This is like the 5x5 where we have the I have to go back to the equation, but this is just the matrix of the Bernstein, or of the quadrature points according to the Bernstein equation multiplied together to fill this basis.
Okay, so what is the column? Is that corresponding to the quadrature point or the basis?
This is
it all the basis functions evaluated at one quadrature point or the other way around?
These are the weights. Yeah, so this is one quadrature point. This is each different quadrature point.
So you have 5 basis functions, so your fourth order.
Yeah, we're on P4 right now.
Okay. With 5 quadrature points, and then you take that matrix. But don't you have to do the transpose of that matrix then?
Yeah.
It should be the transpose of that matrix, right? The column should become the rows, and then you multiply it. It's the columns. You need to get the transpose of that, right? Because you need to take that first column needs to be dot. It's a dot product between the column.
Yeah, that makes sense because this DP is associated with the a certain quadrature value. Okay.
Yep, and then that will give you. Then what that will do is it will give you a vector UH where it's the UH at each of the 5 quadrature points, and then you can use that.
Okay, yeah, because I have the vector of the UH right now, but if it's, it would be computing the wrong vector.
Well, let's look at that matrix again. Is it symmetric?
Yes.
Okay, then that won't fix anything because conceptually you need to.
It's not perfectly symmetric.
It's not symmetric.
Oh, no, it's not. Yeah.
Okay, good.
There are certain values that are, but like that's not.
Yeah, so that means that you're just basically at that point it's just garbage going into the error calculation. So let's just change that and see what happens.
Okay, so now we're at the e to the negative 16th, which I think looks a lot better.
That's perfect.
Okay, good.
That's so close it makes me suspicious. I guess we'll see. It should be pretty good, right? Like what is it? What does the key say? It's probably your fourth order polynomials, and it's just the sign from 0 to 1, which almost looks like a linear. So I might believe that. Can we try it with like degree 1 and then go to degree 2 and then so on? So do degree 1, the error should be bigger.
Still e to the 16th.
Yeah, so I don't know what you're outputting there, but there's still, so go down to the, you have the transpose of UHB what are we doing here? What's f? Is that just a sine function?
Yeah, it's the sine of x of xe.
And are you sure you got that evaluating at the same points as the UHB? And I mean, it looks to me, from what I'm seeing, that UHB and FB are like the same thing or something, because it's like machine precision. Like, let's just print out what is
There's
FB?
UHB. FB. Oh yeah, it's the same.
Okay, that's a problem. So let's go see where you fill in FB. That looks pretty good. Can you plot FB to and UHB to more precision, like more decimal points, so you can see at what point it differs?
Yeah. What do you mean? What do you mean? How to do that?
I only see 4 digits there, right? It may be different, but in the
Oh,
If you type format long in the command window and then print it out again, you'll get more points there.
and then then run the problem. Yeah, okay, and then type out UHB. Let's compare them.
yeah, they're identical.
So that means you're overriding FB somewhere and setting it equal to UHB after you, I mean, can you print out FB like right after you set it to sine? Like go down, yeah, FB, right? Three lines down. Take the semicolon off on line 36 so that you can print that, and then we can see if you've overwritten it somewhere. So now you're printing FB twice, right? But at 2.
Let me just clear and start over. So that is the FB of just this section when I created it.
And then what is it at the end?
Yeah, I don't remember anywhere where I override it, but I guess it's possible.
It
Yeah, but-
seems to me that there's a mismatch between the number of points that FB has and the number of points that UHB should have. Because wasn't there like 5 on UHB and there's only like 2 on FB?
We switched it to a degree 1 right now.
Oh, I
And
must have
so,
missed that then.
yeah,
All right, never
UHB
mind.
should have just the 2 as well.
All right. I missed that. Sorry.
Yeah, that's all right.
Yeah, so what the heck is happening to your FB? So online, yeah, go ahead, Kyle.
Should there be more quadrature points for computing the error? Because really all that we're doing is we're getting the error at 2 points.
Yeah, because the
and-
sine function is yeah, can we do linears with like 5 points or something?
So just keep it at the
So degree
at
the base
P1.
will be degree 1, but the number of quadrature points
Yeah.
will be equal to some other value that you can set. So when you pass into that function, not P.
Oh, just some other value. Okay. Yeah.
Go back, and then when you compute quadrature points and weights, don't pass in P. Pass in something else that you can set. Yep, there you go. Like 5. There you go. But I really doubt that even with 2 points, I don't think the sine function and a linear are going to be, I mean, they're not going to be the same, are they? Is the function x?
Well, if you think about it, we're minimizing the inner product at those 2 points.
So maybe they're actually the same. Maybe it passes through the sine function right at those 2 points.
That's what I think is happening.
Yeah. So that would mean that, yeah, you need to compute at many more quadrature points.
Okay, so with that, error is now
There you go.
178. Okay.
So now
So-
let's go to degree. So why don't you keep your quadrature points at like 8 points?
Okay.
Constant. So put that at like 8, and now let's go to degree 2. So let's run degree 1 first. Put that at like 8, run it. Let's look at the error.
So now, looks like it stayed the same.
Okay, that's fine. Now let's do degree 2.
I'll show you a picture. They're really smart dogs.
Okay, it
It's
dropped.
getting smaller. Let's go to degree 3. Yeah, great.
Okay, it's small. Okay,
Yeah,
great.
remember your integrand has a sine function in it, right? And Gauss-Legendre is only exact for polynomials, so the sine function is not a polynomial. So you have to always use higher order quadrature for that, for the error integrand.
Okay. So for our homework that we did when we had to determine how many quadrature points we needed to use for like a 6 power, that's because it was a power we could use only 3, but because it's a sine we have to use a lot more. Okay.
That's exactly right. Yeah, that would be a good. Can one of the TAs hop onto the third topic and at the bottom in the to-do section, make a note that we probably just need to have an example error calculation where we talk about all these subtleties.
Yeah, I'll jump on and do that.
So you're talking about using additional quadrature points. So when I was looking at the Gauss quadrature, there's hard-coded in 3 of them.
Yeah, we added a link to a place on the web where you can get like, I don't know, up to 16 points to machine precision or something.
But
Because all
hard-coded
the-
in?
Or, yeah.
Yeah, hard coded in. They're just tabulated.
Okay.
Just so you know, Mike, we already added that as a to-do at the bottom of this page
Did
That was-
we?
that we talked about a couple days ago. So
Okay, good.
Oh, yep, there it is.
Great.
Thank you so much.
Okay, who is next? And they can be other questions too, like higher level questions, just about splines or IGA or, doesn't have to be the homework. So are we then done for the day? Is there anything else?
I just didn't want to take up anybody else's time, but I do have a question all the way back at the first set of problems.
Okay, great.
On problem 7, it says determine if the vectors n1, n2, n3, and then the other ones n1, n2, and 3 form a basis for R3. Hint, analyze the null space of the matrix whose columns are composed of the given vectors. So I did that, and the null space comes back null. So I'm just like, I don't know what's going on here. I'm not quite sure what.
What I meant was like on a piece of paper. Not are you using a program or something?
Yeah.
Yeah. Let's pull that one up. Let me share my screen. Let's look at it. Problem.
And are you asking if the first three form a basis for R3 and then the next three form a basis for R3, or are you asking if combined the two of them form a basis?
Okay, let me just jot down a few notes for you here, Eric. Let me see here. So, all right. So here we are. This is one you want, problem 7, right?
Yep.
All right, so what I'm saying is if I give you these 3 vectors and then these 3 vectors, I want to know if they form a basis for R3, and the way that you do that is you analyze the null space. So what this means is if and I say analyze the null space of the matrix whose columns are composed of the given vectors. So if we take a look at the first 3, I'm saying we put n1 as the first column, n2 as the second column, and n3 as the third column. And then what I mean is by analyzing the null space is you need to solve this problem. You need to solve for the coefficients A, B, and C such that it equals 0, 0, 0. And if you can do that, if you can successfully solve these 3 simultaneous equations and you get A, B, and C, then and A, B, and C are, so if you solve this matrix, these 3 simultaneous equations, and you get that A, B, and C are all equal to 0, then you know that the null space is empty. And therefore, these guys are a basis for R3, meaning there's no linear dependencies amongst these 3 vectors. That's what this calculation is showing you. So this one is, so why does this one work? This one is by, you can look at this one by inspection. Why is that?
No, because they're all orthogonal to each other. You can see that.
Yeah, it's just the identity. We know that the identity is a full rank matrix. If you were to solve, you would get that A equals 0, B equals 0, and C equals 0. The next one is not so clear. And so you actually have to go through the process of doing, you know, what is it? The row reduction. What is that method? What is that? I'm drawing a blank. It's, what do they call it in like?
Row echelon, maybe?
Yeah, you gotta do, that's right. You gotta put, so you're gonna start out with 2, 1, 0, 1, 1, 1, 3, 0, 5. And you need to put this matrix in what we call reduced row echelon form. And if you can do that, if that's possible, right? In other words, if you do that, you're going to get the identity matrix, and then you know you're good. If through that process one of these diagonals ends up as 0, then you know that this is not a full rank matrix. In other words, the null space is not trivial. It's not the 0 vector. So that's the idea behind this guy. And I don't know what Shihui wrote. Yeah, so I'll have, he needs to come in here and add a few more details. That's not very helpful. Let's add that. I already have that, add more detail. Okay, so it's basically like just understanding what the null space is, and then just using some basic undergraduate linear algebra. What is that method called? Oh, it's gonna drive me crazy. Let's look it up here. Gauss elimination. Gauss elimination. Yeah, you do Gauss elimination, and if any of the diagonal entries end up at 0, then you know your matrix is singular, and therefore the null space is not empty, and those vectors are not linearly independent.
So basically, the null space needs to come out to be 0, 0, 0, or the answer to that needs to come out to be 0.
Yeah,
0, 0.
in other words, for those vectors to be linearly independent and therefore form a basis for R3, the only guy in the null space can be the 0 vector. Which means, and another way to say that is that if you solve that system of equations, then A, B, and C come out to be 0. And the way you solve little systems of equations is through Gauss elimination. If you remember from way back when, what Gauss elimination says is you put like 2, 1, 0, 1, 1, 1, and then 3, 0, 5, and then you do this augmented matrix thing where you'll put 0, 0, 0 in there, and then you'll do Gauss elimination on this. And if you're able to transform this matrix into a matrix where essentially it'll be like 1, 1, 1, 0, 0, 0, and then this 0 vector then will be turned into A, B, and C through like adding rows together and multiplying and, you know, adding them together. Anyway, it's Gauss elimination. All right, did that answer your question, Eric?
Yeah, and I'll go and look at it closer to figure out why, because I like to know why codes don't work the way I expect them to work. So I'll find out why null space didn't work.
I think it did, Eric. Saying that the null space is null
is exactly what you want. It's null. There's nothing in it. That's right. Yep.
Because if it had returned some values, then it would have mean that it's not a basis, because then A, B, and C would actually equal something.
That's right.
I would have expected it to come back and equal 0, 0, 0.
But that's the same thing. Mathematically speaking, we say the null space is null if it only contains the 0 vector.
I see. Okay, that makes sense.
Mm-hmm. All right, any other questions? Okay, well then let's stop 5 minutes early in celebration of the fact that it is Friday. How does that sound? All right. You guys are a quiet group.
Thank you.
Yeah, no problem. I'll see you guys. Have a nice weekend. We'll see you on Monday.
Yeah.
All right, thanks.
Okay, bye-bye.